Third, we're going to learn about maximum and minimum, global and local. Local first. As a last application of gradients, you might ask, in which direction does f increase the fastest? Actually, you already had this question in your homework. I saw that in 11.5. So in the Mario Kart, which direction do you have to drive in to get first to the finish line? Drive in to get first to the finish line. That English is confusing. So, do you know the answer? Because your homework already asked this question. What's the question? What is the fastest increase or fastest decrease? Which direction? How to find that? Do you know? Gradients. Gradients basically showing all of this. So let's have an example. Consider f of x and y, x squared plus y squared at the point 1, 2. In which direction f increases the fastest? So definitely it has something to do with gradients. Gradient tells you, the perpendicularity of the gradient tells you literally the fastest increase, the fastest decrease. So we just need to figure out the total thing now. Also, I copied from the Wikipedia this interesting note. It's called del operator. It's a nebulous symbol. People usually call it del. Fact. The fastest increase is in a direction of the gradient. So you need to find gradient at the point, right? Of the gradient of f. You don't even have to write this down. So in general, that's not even for the specific question. The fastest increase and decrease is in a direction of gradient at the point. So like I told you, if you are at the edge of the cliff, it will tell you to jump from the edge of the cliff. Luckily you have a parachute, but that's true. Instead of walking around the mountain, why not just jump off this waterfall, right? Yes. Yeah. Thank you. No, definitely let me know. Let's see what we're talking about. We're talking about the circle, x squared plus y squared equals f. That's a circle, right? Depending on f, it has different size. So when we fix some kind of f, we'll have some kind of circle. So you can draw a circle. And then it asks you, which direction should I go? Of course, I should go the direction of the gradient. And you can find it. I will skip how we found it. Derivative with respect to x, that's a derivative with respect to y, plug the point. That's why it became 2 and 4. This is fixed one. When f is 5, we got some circle. So you see, that's the idea. Jumping from the cliff, literally in this case, means going perpendicular. This makes sense because on the level curve, x squared plus y squared equals 5. 5 is just an example. F is a constant, so to increase fastest, you need to point away from it. Let me show you again. Here are the different circles. F equals 7, 10, blah, 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 right? So F is different. When I'm walking on F, here, level curve is where the height is not changing anymore. That's literally the whole point. When you fix this number 5, that's kind of the height of 3D object, the height of the mountain, for example. So on that height, if you're walking around the mountain, guess what? You're not getting down the mountain. Makes sense? If you keep walking around this hill, you're not changing the altitude, so you're walking in circles around the mountain. Let's say this is a valley, right? So you're walking in the valley, you're not climbing the mountain. How to get off the mountain or get onto mountain? Well, duh, you go perpendicular. You have to escape the circle in order to go up or down. That is why it makes sense that gradient is perpendicular to the level curve, and it shows what to do. It points away from the level curve. Oh, you see, I forgot I have this example. In fact, if you're on a mountain or cliff and your friend says to jump from it to the ground, you usually jump perpendicular to the mountain and not tangential to it. Yeah, that's kind of what I said. So if you jump off the cliff, you're not jumping. I guess if you're smart, you're not jumping off the cliff. But let's assume you have parachute. Let's assume you're a professional, right? Then you jump off, not to the left or to the right. So what is the biggest rate of increase of f? In your homework 11.5, they already asked this question. That's the size of the vector, gradient vector, which means magnitude. The biggest increase or decrease is magnitude magnitude, or size of the gradient. If gradient shows you where it is faster to jump, move, fly, then the size of it will tells you, well, what will be the biggest change. Does it make sense? Those kind of some, bless you, classical ideas here. Do you remember what magnitude? Maybe you should write down. You write down, and then I'll write down after you. The magnitude. What if at some point you will have so many cheat sheet formulas? Do you improve your formula sheet slowly? Someone should post in the forum, and I'll post it in the Canvas. We can share the one with best handwriting, or in general, like beautiful. Because creating the formula sheet is really important for this class. So that is one of the oldest formulas. A square root. Yeah, what's inside? Vlad, did you want to say? Did you want to say?
I wanted to ask.
Oh.
So let's say, like the fastest way to get down from the cliff is to go perpendicular, but all of this is only if the speed is constant for both.
Yeah. For now, we don't increase the dimension. So every time you increase some kind of idea how fast, the question is if the speed is different of you. Yeah, then it increases one more variable. Usually it's a product of that times. So you still will have the faster way out, but then your speed will change the direction. Yeah.
But if the speed of going circles and going down is like really big speed, but the speed of going perpendicular is slow.
But you still want to get out. If you walk in circles, you never change the altitude. You either to go up or go down. So if a turtle is trying to go up and down, and you're very fast running in circle, turtle still wins because it's go down or up or down. If the goal is to change the altitude, then someone should go perpendicular. That's a very good question. What was inside of the square root? X squared plus y squared plus z squared, where those are coordinates, right? So, but then we know the coordinates are derivatives, remember? I don't want to change the formula, but because it's del gradient, it consists of derivatives. So I showed you that. See, it's always perpendicular to the mountain curves, level curves, like so. And then gravitational forces, same thing, called gradient descent, gradient ascent, and so on. I'll show you more later. Now, finally, welcome to the highlight of the chapter on partial derivatives, because now, in the next lecture, we will learn how to maximize and minimize a function of several variables. The good news is it is similar to whatever we learned in Calculus 1, single variable calculus, where you need to find critical point and use second derivative test. We had first derivative test and so on. But this time, we will have a little twist. Goal. Basically, example. So make a topic. Which one do we do? Local. Local, mean, max. Synonyms in English books. Local extrema, local extreme values, local minimum maximum, and there was something else we will see. They never agreed on how to call it, so you will see different notation. Example. It's easy to show with the example and to show you how to do it. So let's try to do it. In this picture below, F has a local... Oh, that's just an example. Fine. F has a local maximum at 5 and local minimum at -1. Let's show you this. This is a 3D object, basically mountains, right? This mountain over here collects the water, but then also have a hill and so on. So just like in Calculus 1, it has minimum and maximum. Some of them are global if this is the biggest hill or the smallest pit. And then some of them are local. Local minimum at -1, that is z, right? So z equals -1 is local, that did not fit, minimum, local minimum, and then 5, z equals 5, local maximum. To find out if it's global, you have to check if it's ever gonna go higher than that, and it does go higher, so it's just local. the coordinates used to be 1 point. Remember, it was input and output. Well, now the coordinates of input has x and y. It makes sense because it's in 3D. Does it make sense? Just quick explanation visually. And now we're going to define everything and do the example. So, definition critical points. A point is called a critical point. I'll call it CP. CP. We also call it a stationary point, but actually that's not true. Critical point, American books do not agree on that. So, critical point usually in calculus 1 we learn derivative is 0 or d and e. In this case, we're only going to have the one that's 0. So we only if. So let's write down if. Partial derivative is 0. Partial derivative is 0. Or one of these partial derivatives, d and e, does not exist. So remember in calculus 1 we take derivative, set it equal to 0. Well, now we have many derivatives. So we're talking about partial derivatives now. The theorem says that if f has a local maximum or minimum, then it is a critical point. Critical point called critical because something is happening there. But we remember that critical point is a candidate to be min and max. So instead of checking infinitely many points, we just find the critical point, CP. And just check those. If none of them are max mins, then we move on. Remember, max mins may be where derivative doesn't exist. That's called a cusp or sharp corner, right? That's also possible. So instead of smooth minimum, you might have a minimum at a sharp corner, like absolute value of x. That's why d and e are also included. At the critical point, a function could have a local minimum or local maximum or neither. So it's a potential candidate for the max min, but it's not necessary that we will have anything there. Basically, almost the same thing we had before. So but now we will use partial derivatives. Okay, now let's do this. Let's see. Critical point. Let's define how to find it. So let's see. You have to write it down. That is very important. Let me read you. F is continuous, has continuous second partial derivative. So we're going to be using second partial, we don't call it second partial test, but it's fine. This book did. Second partial test, second derivative test, second partial derivative test. That's how it's called. But to use a second derivative test, functions should have second derivatives. That's kind of the idea. So continuity here is important. So it has differentiability is important. F is continuous, have continuous second partial derivatives on an open region containing, or open interval region, it's fine, containing a point AB where both derivatives are zeros. Both derivatives are which? Partial derivatives are zeros. And I will add or D and E. We just included this in the definition. 0 or D and E. Let me put them in the box. Then we have to test them to figure out if they give you min or max. The test for relative extrema has the formula. D equals, this is my nice notation, fxx fyy, so second partial derivatives, minus fxy times fxy, and that's when we're using them squared, like so. And you plug the points in. So their formula is more professional because they plugged the point A and B in. My formula is easier to memorize, that's why I like it for. fxx fyy minus fxy squared at the point. And then the most important, to check the sign. Just like in calculus 1, we're checking signs of test points. Here we're going to be checking the sign of this D. If it's positive, then we don't know yet. It's positive in two different cases. It might give you a minimum or a maximum. If D is positive, then after this, let me change the color, we need to check fxx sign. fxx is positive or negative. If it's positive, then it's minimum. If it's negative, then it's maximum. If D is negative, then it's easier. We just claim it's a saddle point. So let me highlight relative minimum, relative maximum, a saddle point. And it's inconclusive if D is 0, then we don't like it. Then we say there's no info. I will make more notes, but I wanted to first finish copying it. So that's going to be the most important part on a test. She did not give me the exam 2 yet, but I checked previous years and I already see 2 problems there on this chapter. So definitely it's very important. Local minimum, local maximum, critical points. So let me write down. These guys here, partial derivative that equals 0 at the point, are critical points. 0 and D and E are critical points. Let me put D and E. I also want to point out that the formula for D, I'll be back, don't worry. Let me move this here. The formula for D is easier to memorize like so. It's a determinant of 2 by 2 matrix, which is not too bad. fxx, fyy, fxy, fyx. That's where the formula comes from. Cross product minus cross product. So fxy and fyx are the same by Clauser's theorem, which we learned last time. That's why it's squared. I'm talking about this beautiful formula. Yes?
So on the last one where you have D is equal to, is that like a 0 or is that just like if you can't solve?
D is 0, then there's no info, we have to use another method.
Okay, so that's a 0. Okay.
Yeah, that's a good one because then you don't have to continue. But then it's also bad when you have to know other methods. Maybe just numerically, you can figure out numerically, and there are other mathematical methods too. So D, remember, 2 by 2 matrix determinant is cross product minus cross product. This D is okay, now I'm confusing you. It's small d and big D, and that's the same thing. Usually I call it big D. It consists of partial derivatives. Finally, it's kind of hard to memorize it, but I will show you this way. Relative minimum. This is how I teach in Calculus 1 class. You might actually appreciate it. Here it is. If it is local minimum, then D is negative and fxx is negative. Then it's local minimum. Do you know how I teach it? So D is negative, that's minus. Fx, oh, is it positive? Sorry, yeah. I'm thinking about the other one. D is positive. Fxx is positive. So that's why how I'm saying it, plus, and this is a smiley face, right? No, seriously though, it's very interesting. It works. This is the smiley face of a 3D object. You see this bottom? This is a tongue. It is minimum. That's how you can memorize. If it's a smiley face, the smile gives you minimum because D is positive and the fxx is positive. However, if D is positive, but then fxx is negative, because someone shoots someone's eye with like a rock, right? That person is not happy now. Then it's grumpy. You see? No, see, look at this. It's grumpy So the nose is a maximum. That's literally makes sense. And then the mixed one is a saddle point. That's a new thing. The mixed one is, if the first one is negative, then you don't even have to check anything else. So I don't have any idea for that one. If it's negative, if D is negative, then it's a saddle point. So let me continue this idea. D is positive, fxx is negative. D is positive, fxx is positive. Smiley face and grumpy face. That's how I teach in calculus 1, first derivative test, and they like it. Actually, my student is taking class right now, calculus 3 class with another professor. She was explaining this, and he's like, "Oh yeah, it's a smiley face." She's like, "What?" Because it was my student. So that's how she also learned about a smiley face. Yes, the matrix. Here you go. Okay, now let's do the example. And you will see how not fast it is at all. That will be lots of things to check and lots of cases to check. Do we have time? Yes, we do. Yeah, I'm not gonna scare you, but that will take like 20 minutes for one problem. Let's do it. Are you done with this one? Okay, let's concentrate for this one problem. I highly recommend you, and then I will show you more stuff. You see, local maximums, global maximum, pretty cool idea here. Dun, dun, dun. Here it is. Let's do this nice, good quiz exam question. Find all local minimum, maximums, and saddle points for this surface. Again, it's all three-dimensional objects now. X cubed minus 3x plus 3xy. So remember, very interesting, we have x as an input, y as an input, which is run and rise. That's American thing, run and rise, right? Change in x and change in y. Left and right, up and down. And the output, right, which is this z, that's height. Height is z. So it's completely different perspective now versus we had it in 2D. How are we going to do that? Solution. First, I will give you steps. I like teaching with steps. People like steps. You don't have to follow my steps. That's not required. But my steps help during the exam to recover what to do next. So I like teaching with steps. First, find critical points. Set them equal to 0, D, and E. Where the critical points, where the partial derivatives are 0 and D and E. That's the definition. Well, by definition of critical points, we need to find partial derivative with respect to x, partial derivative with respect to y. You have this partial derivatives are today on the quiz. You should be good at this by now. What is partial derivative with respect to x of 3x of x cubed minus 3x and blah, blah, blah? 3x squared minus 3 plus 3y squared. Last time I will explain for people who missed the classes or got sick. Check it out. When I'm differentiating with respect to x, everything not x is a constant now. So I'm looking at x and I see variable, variable, variable. Y squared is a constant. So derivative of 3xy squared will be 3y squared times derivative of x. But derivative of x is 1. That's the idea here. And now you switch. Derivative with respect to y. Everything else is a constant. Y is only here. So everything else gives you 0. X cubed gives you 0. It's a constant. Minus 3x gives you 0. And the last piece gives you 6xy. I like to put it in the system, but you don't have to. Now we solve it. When does it equal to 0? Or D and E. D and E happens with fractions. I don't see a fraction here. So there's no D and E. D and E is when you divide by 0, usually. So there's no D and E points, just the 0 ones. Okay, you have two systems here, so you can solve it. Two systems with two equations with two unknowns. Solving 6xy equals to 0. That gives you two options. X is 0. Or, and y is 0, right? Remember, 6 is not 0. Sometimes business students ask, no, you don't know. You're smiling. Business students ask me, if product gives you 0, remember the rule from school, right? Then you set all the factors to be 0. And so they ask me if 6 can be 0. And that was very unusual to explain that 6 is not 0. I don't know, like it's kind of, that was very confusing question. I'm very respectful, like, okay, 1, 2, 3, 4, 5, 6. It is not 0. I don't know. It's hard to explain that 6 is not 0 somehow. It's easy to do this, right? Very interesting questions I get from some classes. Now, the thing is, it's and or. So I will have to figure out what happens with y over here and with x over here. How to do that? I'm going to plug it to the first equation. Let me number them. I like numbering equations. Equation number 1, equation number 2. From equation number 2, I got that x and y can be 0. Those are definitely critical points. Critical points, CPs. But now, I have to figure out different cases. What happens from equation number 2? Okay, from equation number 2, no, number 1 actually, number 1. We're going to plug x equals 0 first. X equals to 0. Then, the correct notation is partial derivative of x at 0 gives you 0 minus 3 plus 3y squared, right? That just decreased the dimension. When I plugged a fixed point for x, now we have just again 2 dimensions. It's just a parabola. 3y squared minus 3. But to find critical points, we again repeat the process. Set it equals to 0. Solve it. Minus 3. Let me not change the color. So set it equal to 0, right? Or D and E. Or D and E. But, you know, it's a polynomial. It cannot be D and E. Minus 3 plus 3y squared equals to 0. Solve for y. Y has a solution. It is 1. Yes, no, yes, no. Plus or minus. I always say in calculus 1. If you miss the minus 1, some panda is crying somewhere. Panda is crying. Don't make panda cry. So make sure you have 2. Plus and minus 1. That means now we have 2 points. Thus, therefore, thus is the shortest one to write. We have 2 critical points from this first guess. Remember, x was 0, so it's 0 comma something, 0 comma something. And then we found, let me put it in pink, y. Y is 1 comma n minus 1. Put it in the box, we will need this. This. Put it in the box. We will need all the points. We just found 2 points. Now we have the second case. What happens when y is 0? Repeat the whole process. Again, it's equation number 1. We did not change that. But now I plug y equals 0. Partial derivative with respect to x at 0, but that was x equals 0. Now it's y equals 0. Equals 3x squared stays. Minus 3 stays, and then plus 0. Set it equal to 0. Solve the equation. 3x squared minus 3 equals to 0. Same as before, x squared equals 1. X equals plus or minus 1. We have 2 points again. Thus, we have 2 more points. Critical point is, this time we fixed y variable. Y was 0, and we were looking for x. So I will write down like this. Y is 0. Y is 0. And then in blue, let me wait a little bit. I think it's too fast. Let me know if I'm moving too fast. We basically solved, we used one equation to find x and y. And in each choice, we plug into another equation. And then another equation gives us solution, sometimes more than 1. So we have 1 and minus 1. More 2 critical points. So those are 4 critical points. put it in the box. Nicely, it's nice to rewrite them all four, but I just put them in boxes, so why do you need to rewrite them, right? So if you want, you rewrite all 4 points. We'll be testing them all. Each of these critical points can be min and max, or none of them. That's actually the most upsetting case, if none of them give you anything interesting. So we will test them using second partial derivative test. Yes?
We do the exact same thing for
F of y?
Yeah.
No, but it's different, right? Oh, you mean, should we keep plugging?
Yeah.
No, from here we solved it. You can try. If you plug 0, gives you 0. If you plug 0, gives you 0. So we used the second one to find some options. You can use first one to find options, but it's harder. So we use the easy one. Good question. So we basically used once the second equation, and from there we plugged everything into first equation. And we got 4 points there in yellow boxes. Okay, that was just step 1. Now, let's see. That was kind of step 1. That was a long step 1. Find critical points. We found 4. Step 2. Let me put it in a circle. Step 2. Test. Oh, you're gonna shut down. I already can see that. Lame. Don't do that. Test each, you can write down, test each critical point. Test each critical point using, guess what? Second derivative test. Second derivative test. And then in that book, they call it second partial derivative test. But we're working in 3D. Duh. It will be partial, so I don't see a reason to write this down. So critical points are candidates. Testing them means we're going to check if those candidates are critical points. Test these candidates. Test critical points. Okay, you need to build. So step 2 has a sub-step. To test them, we need to build or create D. I like to use it capital D. D consists of partial derivative xx, fyy. I like to put those first. Xx and yy. Then xy and yx. This is a very common idea in applications of math and physics and engineering and pure math to create this kind of matrices and determinants. See, the row, if you don't know in English, row is this line, right? Row. Maybe I should write down. Row. Row has axis. Row is in charge of axis, which makes sense because it's run. It's horizontal. While columns are in charge of y's. So as you see, columns are changing y's, while row are changing axis. Something like this. Or you can see it that the first one has x's first, the second one has y's first, and so on. Very classical idea. Now you hope that it will be easy to find. In this case, it is. If you don't remember, it's actually handy to rewrite the original function first. But you don't need to do that. Oh, we don't need the original function anymore. We need first derivatives. Remember, fx we found was 3x squared minus 3 plus 3y squared. Fy was 6xy. So from there, I'll right away find all second derivatives, all possible second derivatives. Are you still with me? And people at the back, try your best not to get distracted with phones. I know it's very hard. Once I sat down on a beanbag with my phone, I opened TikTok, accidentally 2 hours passed. I don't know how it happened. Yes?
Okay, so like what happens though if like your second equation isn't simple enough, like 6xy, to get the x and y?
Oh, the solving part.
Yeah.
You're asking what if solving is hard? Yeah, that happens. A very good question. So it seems like we solved so easily. But what if solving was not easy? Then you basically struggle and cry, and then you... But then, like, it's not you, right? Like, we all struggle and cry. That's how it works. Luckily, for homework and exam, we'll give you something very easy. Usually polynomials. But if there's a fraction, square roots, basically, you're screwed, right? So you have lots of methods how to solve equations and blah, blah, blah. Good question, yeah. It can be very hard. So some people do master's degrees on that because sometimes it's very hard to solve, figure out what to do with the testing and everything. 3. Okay, did you finish table by yourself? Oh, good job. Let's do it. fxx, tell me fast. fxx is 6x. fyy,
6x.
6x. I like to do those first, but you don't have to, doesn't matter. fxy, 6y, fyx. Those are the same. They should be the same for continuous functions. Did you get it? How we built this amazing, beautiful table? So now the matrix is very simple. You know how to solve this. The matrix is cross product. 6x and 6x, I will do 6x times 6x minus 6y times 6y equals 36x squared minus 36y squared. Put it in the box. That's D. D not at the point yet. So it's a general D. No, this one is just polynomial product. Clever question. Is this actually a dot or a cross? It's a dot in this case, just a normal product between polynomials. Very smart that you asked that. So we have this D. Remember we wrote this formula over here? I do not appreciate it how hard it is. This is a clever way, this is official way how to write down this formula. But in general, I don't remember this formula. I remember how to solve the 2 by 2 determinant. And the shape of determinant is pretty easy to remember. X, 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 Y, Y, X, Y, Y. So that's why I do not recommend to memorize this formula. But it is exactly what we need. Fxx, Fyy minus Fxy squared. So that's what we just got. Now we're going to do smiley faces and grumpy faces. So it's getting there. This is my D. This is what I got. Before we can check the sign of this beautiful polynomial, we need to plug the point. There's no sign until you plug something. So that's the last part of this amazing problem, which takes 20 minutes. Step 3. Plug the critical points. Plug. Substitute. It's a professional way to say substitute. All critical points into D. Check the... Okay. Let's plug. We're going to check signs separately. I'll change in blue. Check it out. So we have 4 points. 0 and 1. Let's put them in columns. 0 and minus 1. 1 and 0. That will take more time. And then minus 1 and 0. So that's me. Minus 1 and 0. Anyway, I'm not sure how much space it will take. So I think more. Remember to plug carefully. Maybe your brain still is getting used to several variables. So maybe write down this is X, this is Y. Now your brain knows where to plug and where. Don't make this small algebra mistake. It will be upsetting to mess up at the very end because you forgot what 3 times 5 is, you know. Definitely be careful with that. D at 0, 1, plugging in. So 2 ways to see it. Different teachers teach differently. I will show you both. Either you plug it right away into the determinant. Some people do it right away here because it's not that hard. 0 and 1. X's are zeros and Y's are ones. And then it's just 36. Or you plug in the box, let me call it star. Or star. You can plug there too. D is X is 0 minus 36 times 1, 36. Both are fine. You choose which one you like to do. I see students do both, so that's why I want to explain both. Maybe. Yes, it is negative 36. Good job. I didn't do this mistake on purpose. So we just finished our hiring process. We hired 9 more teachers, professors, just like me. And I'm in a hiring committee. And one candidate was interviewed, and then she was presenting how to teach. And then she made the mistake, and we pointed out the mistake. She's like, oh, I'm so sorry. Oh, it's such a bad mistake. I'm so sorry. So I told her, never apologize. Either lie, you did it on purpose, or like, yeah, good catch. Like, why do you apologize? She's like, really? Like, I can do that? Yeah, you can do that. Anyway, I'm teaching bad stuff to people. Not to be polite. She was apologizing so much. Teachers do mistakes a lot. That's actually the whole point of that. Okay, let's speed up. We're gonna check the signs later. Let's plug everything in first. Or both notations are fine. Let's make a conclusion right away. There's only one case we had when D is not positive. What is that? Saddle point. That's the best one because then you don't have to continue. Yay, it's a saddle point. The middle of the saddle. Saddle is literally that thing on the horse. Point 2. Let's quickly plug the 0 and minus 1. I'll plug into the polynomial. At 0 and minus 1, will it change anything? No, still minus 36. Nice. Negative. Saddle point. So that's the pleasant ones. When you get negative, I like to put on exam the saddle point because then it's like very fast. But usually we try to put both saddle point and some kind of min max. And now the long ones. The long ones will be either nothing or min max. The next point we found was 1 and 0. D at 1 and 0, plugging into polynomial or original matrix as well, gives you 36. That one is positive. If it's positive, we have two cases. I already know that one eye is open, right? Now everything depends on the second eye. If the second eye is open, it's a smiley face minimum. If the second eye is closed, it's a sad face maximum. Does it make sense? Like a childish way to memorize. Surprising helps lots of people. So we check this sign after this. Let me change the color. Check. Let me make it fat. Check fxx sign at 1, 0. The sign of xx now will define. Well, now I need to go back and find the xx. I never even solved it. I just like put it right away into the determinant. But I remember that this is the one. In general, remember, put it in a circle here. And maybe in the formula where you put it at the very beginning. Circle this guy. This is the one that gives you minimum or maximum. This is the second step. fxx sign determines min or max. If D is positive. Well, 6. So usually people write down like this. 6x, parentheses, a bar, 1, 0. That's a professional notation. A bar means at. 6x at 1, 0. That gives you 6. Let me write down. 6 times 1, which is 6, which is positive. Now I can complete the smiley face, which I will use the same color, purple. Smiley face, it smiles, so the tongue at the bottom is minimum. And I can conclude local mean. Now I'm going to stop and ask you. Did you get this part? What do you think about that? I will surprise you. We do teach it to business calculus students. There's a calculus 2 for business students, and this is what we do. We don't tell them it's calculus 3 not to figure them out. It doesn't say that. It's just like chapters. It says multivariable calculus, but they don't know it's calculus 3. So we teach them this because in business and statistics, we need to have more dimensions and lots of investments and stock markets. They actually have that. So we teach them how to find that. They hate it a lot though. But they handle it. I have to say, many of them do. Yes?
You put it back into fxx because you had the variable x in your point.
So I think I know the question. First, D was positive. Right. Then I had to have an extra step. I always check fxx and plug the point in. If there's nothing to plug, that's 0. We had x to plug in, so we plugged x.
Right, but why is it fxx instead of fyy?
Oh, that's part of the theorem. Very good question. That's theorem proves that we only need fxx. That's the question, yeah. That's part of the theorem. You can check it out the next time in the book if you want. People are like, no, we don't want. Last point. -1 and 4. Last point. D at -1 and 4. No, 0. Why did I say 4? 0. Is. What's the sign of that D? Positive again. So D let's see, D equals 36 positive again. So I don't know. So I have to go to sub-step. Check fxx at minus 1, 0. This time it's minus 1. So it will be minus 6, right? Minus 6 is negative. And that's how we have all the 3 cases. And that's why this problem is so long. It has all 3 cases. Let me be consistent with my colors. Like, wow, okay, people are getting sick. Minus 6 less than 0. Then I know how the smiley face will look like. The first one was positive. The next one was negative. That gives you sad face. And the nose is maximum. Did I mention that why it's maximum? The tongue is at the bottom of the pit. So it's visually minimum. The nose is at the top of the hill. So it's visually maximum. That's how you should remember it. Then it's local max. In 3D, we just located all the mountains and all the pits. And we can write down the conclusion. Oh, wow, I don't have space for conclusion. We can write down the conclusion. Write down conclusion or answer. Let's do answer. Answer. And this is how professional people usually write down the answer. Answer. Let's see. Saddle point. We have saddle point, local mean, local max. Saddle point at, we have 2 saddle points at 0 and 1, comma, 0 minus 1. They will ask you, so what's the height of that saddle point? Do you know how to find the height of min, max, and a saddle point? What's the step for that? Plug into the original function. Original f. Plug any. It will give you the same point. 0 and 1. Because they're both saddle points, the height of those 2 mountains are the same. 0, 1 will be the same as f of 0 minus 1. Go to the very original one. 0 cubed minus 3 times 0 plus 3 times 0 times 1 squared gives you 0. So the saddle points are at the level 0. Say it's the sea level. There are 2 saddle points and they're at sea level. Saddle points. Points. Let's make it s. And the second one is, let's do, and then we'll have 2 more. Local mean, local max. Local, which one was first? Mean. Because it was a smiley face. At 1, 0. And then what is the height? They will ask, okay, it's minimum, so how low it goes? We plug f 1, 0, a very original function. It gives you minus 2. That is the height. It's 2 units low, 2 units below the sea level. Also, it's z, remember? That is my z, by the way. Let me put it in red, in pink. This is z. This is z, the height. And the last one, local maximum. There was one hill at minus 1 and 0. How high that hill was or is, f at minus 1, 0, plug it in, gives you 2. So it is 2 units above the sea level. So it actually makes sense. Sea level plus 2 minus 2. That is z. Set 2 saddle points, local minimum, local maximum. To check, we can actually try to plot it. Some programs do plot it. Actually, some of the classmates posted in the forum 3D plotting tools. I like using Wolfram Alpha. Let's see if it handles. Plot z equals x cubed minus 3x plus 3xy squared. Let's see if it handles it. Here's a heat map. Oh, it did. Check it out. Saddle point is at the level 0. 0 is over here, as you can see, 0. And then it goes below 0 for the minimum point. If I drop the ball, let me zoom in. If I drop the ball in the middle, that is a saddle point. And then to the right, it goes to the minimum pit. And the height of that pit is -2. So it's 2 units below sea level. And there's a local mountain, height 2, above 2 units above sea level. What do you think about that? Isn't that awesome? It's very tedious, and in general, computers do it for you, but we definitely teach it for you to know what the heck computer is doing. In check, computer says error, I don't know what's going on. It will be your job to go and see what was the bug, how to fix it, and in general, how to interpret it, the result. So I'll put this picture over here to have good note. Questions, concerns, ideas, suggestions? That was just one problem for you to know. Yes?
Is it possible for fxx to ever be 0?
XX, if it is 0, usually D is 0. So when D is 0, we cannot use this test anymore. It was here. We don't give you those examples because, of course, we want to check that you know how to use D. So we usually don't give you D equals 0. But if it is, then we don't proceed after that. You have to use another method, maybe numerical one. So here it is. Here are the steps. I'm not a big fan of it, but if you like it, feel free to use it. Step 1, critical points. Step 2, sometimes people find a saddle point right away. Then, if the D is negative, right, then it's a saddle point. If D is positive, then you have to keep checking. You check fxx. If that one is negative, it's local maximum. If it's minimum, local minimum. If it's positive, local minimum. You can use this way, or you can use the way I did. Doesn't matter, you can be creative. Some people actually relocate all those steps. Just make sure you know how to do it. And finally, there's something here. I already showed you that. And there's a whole Wikipedia page on this chapter. This chapter is extremely important. We don't teach it just to torture people. I definitely can guarantee that. We do teach it because it has limitless applications everywhere. When you build something 3D, mountains, oceans, waves, sound waves, colors, everything has maximum and minimum, and you have to figure out how to find it. Yes?
Sorry, can you go back to those steps where it was
The table ones?
kind of flow chart?
Yeah, the flow. Some people like flows, so I definitely included it in case you like flows. I try to be very versatile in terms of teaching. People have different ways of learning things. It's in my notes. I posted all the PDF files in modules. Okay, people, very good. I'm glad that we handled this.